In this video, we're going to take a look at orbitals and orbital filling diagrams. In purple on the board, I've got Zumdahl's definition for an orbital. It says it's a specific wave function for an electron in an atom. The square of this function gives the probability distribution for the electron. That definition there is pretty complex, hard to understand. Then they're talking about squaring the function and doing probability distributions. We talked briefly about Erwin Schrödinger, and he came up with mathematical equations to try and explain electron arrangements in atoms, and this orbital is one way to look at that. We are not going to get into the mathematics behind that, and I think we are going to use the definition more in green here for our purposes, and we'll say it's a region in a subshell that can hold up to 2 electrons. I do want to talk a little bit about this idea of probability distribution. We've already talked about probability distribution with the electron in a hydrogen atom. And I'm going to pull this diagram back up here, and we talked about this idea about the electron cloud, and we talked about how the electron cloud was the densest close to the nucleus, and then as we got further away from the nucleus, the density dissipated, got less, and we can see that in this diagram here as we get out further away from the nucleus, the cloud is not as dark, not as concentrated. And then the diagram up here is a 2D representation of a 3D model. We've got the z-axis there, and then we've got the xy plane coming out towards you. So it's a 2D representation of what should look like a spherical type object. And that there is the probability distribution of electron in a hydrogen atom. And in the hydrogen atom, we know that the electron would be found in the first energy level, and there's only one subshell there. So that, in a sense, is a probability distribution for a 1s subshell. Let's take a look at the next slide here. And on the next slide, I've got a diagram. And this diagram has got the probability distributions of the orbitals in different subshells. So if we look at the red object right here, that represents an s orbital. And you'll notice that we have a similarity between that red object and this object right here. Similar probability distribution pattern. So we say that this representation here represents the 1s orbital. Now remember, an s subshell can hold up to 2 electrons. So in this case, we have got one orbital. I want to remind you, we got nothing orbiting here. It's a region we're going to put 2 electrons in. So we've got one orbital can hold 2 electrons. The ones we have next in yellow, we have got 3 orbitals, and if you look there, you can see one's orientated along the x-axis, one's orientated along the z-axis, and one's orientated along the y-axis. The P can have a maximum of 6 electrons. Each orbital can hold 2 electrons, so 3 orbitals, each one holding 2, can make a maximum of 6. If we move down to our next one, we've got 5 orbitals for the D. And if each one of those orbitals can hold 2 electrons, that means the maximum we can have in the D would be 10, which we anticipate. And then for the last one here, we've got 7 orbitals for the F. And each orbital holds 2 electrons. So that makes a total of 14. So on the board here, we've got 2-dimensional drawings that are supposed to represent 3-dimensional probability maps of where we're most likely going to find the electrons in these different orbitals. And I realize that these probability maps look fairly complex. Not something you need to memorize here. If you end up taking more chemistry later on in your life, you might get more into detail here. But it is important to remember that the S subshell has 1 orbital, the P subshell has 3 orbitals, The D subshell has 5 orbitals, and the F subshell has 7 orbitals. On the board, we have the complete electron configuration for an atom of phosphorus. What we are going to do is we are going to do what's called an orbital filling diagram. And usually for an orbital filling diagram, we will use either lines or boxes to represent the orbital. So for the 1s subshell, we have 1 orbital, so I'm going to draw 1 line representing that 1 orbital. For the 2s subshell, also an s, has 1 orbital. We'll draw 1 line. For the 2p subshell, we have 3 orbitals. Each orbital can hold 2 electrons. For the 3s subshell, we have 1 orbital. And for the 3p subshell, we have 3 orbitals. So what we're going to do is we're going to fill the orbitals now with electrons. And the way we do that is we use arrows. And the arrows either will point upward or downward. So I'm going to put in my first 1s orbital, I'm going to put 1 electron with an up arrow. And the up arrow, we say, indicates that the electron has a spin in the clockwise direction. And once again, this is kind of a confusing term. Scientists don't actually believe that the electrons are spinning and don't really believe that if they are spinning, they're going clockwise, but that's the notation that they use. So if an arrow is going down, then we say that the electron has a spin in the counterclockwise direction. So our 1s subshell can hold 2 electrons, so we'll have an up arrow and we'll have a down arrow. And then that subshell is completely filled up, so we're going to move up to the next highest energy subshell, which is a 2s subshell. So in that 2s subshell, we have 1 orbital, so we'll put an electron in the up direction and we'll put an electron in the down direction. Which then brings us to our next highest subshell, which is the 2p subshell, and this one has 3 orbitals. Now we fill the electrons in the 2p subshell. We're going to take a look at what's called Hund's rule, named after, developed by Frederick Hund, lived from 1896 to 1997. And it says the lowest energy configuration for an atom is the one having the maximum number of unpaired electrons. So we're looking here to have the maximum number of unpaired electrons. Well, if I go back to this right here, we would say that right here we have a pair of electrons. And right here we have a pair of electrons. So we will apply Hund's rule to our electron configuration. So in this 2p sublevel or subshell, we need to put 6 electrons. So when we enter those electrons, what we're going to do is we're going to put them in unpaired. So we'll put 1 there. Maximum number of unpaired electrons is the configuration of the lowest energy. So we'll put the next one there, unpaired and unpaired. And those all have the same spin. So now what we'll do is we will go back and we will put the other electrons in and then we will pair them up. So put them in one at a time and then pair them up. And then when the 2p is filled up, we will move on to the 3s. Now it looks like maybe here, well, it doesn't really make any difference if I paired them first or unpaired them. They all end up looking the same. We end up having the whole thing filled up. We'll find out later, usually when we end sometimes, it's not quite the case. So if we go to the 3s, the 3s then needs 2 electrons. This one can only hold 2, so we'll go up and then down. And now when we do the final one, or 3p here, the 3p finishes with just 3 electrons. So this is the case I was talking about. Then we will put them in unpaired. So we'll go unpaired, unpaired, unpaired. So right there in that last subshell, we have 3 unpaired electrons. We would say in this subshell we have 6 paired electrons. We have 3 electron pairs. So that's a little bit of an introduction to orbital filling diagram. And then if you know how to do something else, like for example, if I would have given you one more over in the periodic table, if I would have given you, for example, say to do sulfur, I mean sulfur is 1s2, 2s2, 2p6, 3s2, 3p4, so that means we would just have the same exact orbital flowing diagram as this one, but we just need one more electron, and that one more electron would go in the p sublevel, so then we would just go through and we would pair it up, and that would be the orbital flowing diagram then for sulfur. Just have one more continuation, just as we did with the electron configuration.